Hey everyone, we are going to be going over the very first section of chapter 5. Now, most of this happens in the classroom, so there's not really going to be a video, but this is just for you to watch back later if you were either absent or you missed it or you just want a refresher. So we're in chapter 5, we're talking about probability, and this first section is all about randomness, probability, and simulation. After this section, you're going to be able to describe the idea of probability. You're also going to be able to describe myths about randomness and design and perform some simulations. Now, the first activity is going to be an in-class activity where you take a dice, right? And you roll it 7 times for each of the trials, and you record how many times you land on a 6. And then you would do this 5 times, and this would be your simulation because you're trying to see if it's accurate for the problem at hand. We'll talk together about if this, what percent of the time the friends came away with 3 or more prizes, and then does it seem plausible that the company is telling the truth based on what the 7 friends got, or were they just lucky? And you can see the results that we came up with in class to talk about that. Simulation is going to be very powerful for modeling this. Now, probability. Probability is chance behavior. Right? Chance behavior is in fact unpredictable in the short run, but it has a regular and predictable pattern in the long run. This is sometimes referred to as the law of large numbers, right? With more repetitions, the outcome approaches a specific value. Probability describes the proportion of times that an outcome would occur after many repetitions. We, in the world of statistics, write our probabilities as a decimal or fraction. We don't really say percentages too much. So probability of 0 means the outcome is impossible. A probability of 1 means it's certain. That's like 100%. And then everything else must be between 0 and 1. You can't have negative probability, and you can't have something over 1 or over 100%. So to say that it's 110% for sure to happen is not a statistically sound way to interpret something. The next activity that we did in class had to do with flipping a coin. And we saw what happened after we tossed it 10 times, and if it's fair, meaning there's a 50% chance or 1/2 chance for heads and 1/2 chance for tails. And then as we tossed it more and more and more, what did we notice about the overall proportion of heads that we saw? And then we saw later what happened if we changed the probability of heads to 0.3, so then it's an unfair coin. What we saw from that example was something called the law of large numbers. The law of large numbers says that if we observe more and more repetitions of any chance process, the proportion of times that a specific outcome occurs approaches a single value. This is why when people, for instance, my cousin has like 3 boys, right? And my mom was like, hey, if she had another kid, chances are it'd probably be a girl, right? No, that's not how that works. Just because she's had 3 boys in a row doesn't mean it has to be a girl for the next one, right? If she had maybe 300, sure, she's probably more likely to have a girl, but not after just 3. How do we interpret probability? A couple sentence starters. You would want to say after many trials, right? Or you could say that the predicted value after many trials is blank. The key thing here is to say many trials because probability talks about long run occurrences. So if I said the probability of getting a sum of 7 when you roll 2 dice is 1/6, if I want to interpret that value, we could say that after rolling 2 dice many times, about 1/6 of the time we would get a sum of 7. All right. You're going to do, or we did an example on streaks, right? On streakiness, how many times things happen in a row. There's a really good article that I gave you in your notes from the New York Times about streaks, which is really interesting for you to read. So make sure you take a chance and you read that on your own. You did imaginary coin flips, right? So in your head, you wrote out 50 imaginary coin flips, so like heads, heads, tails, 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 heads, etc. And then you wrote down the streaks. So like how many times did you get a streak of 2 heads? How many times did you get a streak of 3 heads? Did you get any streaks where they had 8 heads in a row? Then you used your calculator and use the random number generator on your calculator to do it, and again do 50, and see which one had longer streaks. So some myths about randomness. The myth of short-run regularity. Randomness is predictable only in the long run. So look at these two sets of numbers. Imagine they came from rolling a die. We get 1, 2, 3, 4, 5, 6, 6, 5, 4, 3, 2, 1 versus 1, 5, 4, 5, 2, 4, 3, 3, 6, 1, 2, 6. Which one is more likely? Well, both of them are equally unlikely to get that exact string of numbers from rolling a fair die. Just because one looks, quote unquote, more normal, doesn't mean it's more likely to happen. Also, the myth of the law of averages. Future outcomes do not make up for streaks. Okay, so coins, dice, etc., they have no memories. This myth is why some people gamble, and they keep gambling because they believe that eventually their wins and losses will balance out. This is not how casinos work, and it's not how probability works. Just because you flipped a coin and you've landed on heads 10 times does not mean that you're due for tails. Okay, the law of averages is not a true thing. Now, simulations. Simulations are an imitation of chance behavior based on a model that accurately reflect the situation. Okay, so we already did kind of one of these on the beginning of this lesson with the friends and the prizes under the bottle cap. There's examples on page 290 as well. You're going to be using the 4-step process. This is a thing that we're going to be using the entire year. So the 4 steps include state, plan, do, and conclude. In the state part, you're going to be saying what is the question of interest about some chance process. You're essentially summarizing the problem at this point. You're going to come up with a plan. This is very crucial. You need to clearly describe how to use a chance device to imitate one repetition of the process. You need to explain clearly how to identify the outcomes and what variable to measure. You need to be so clear so that if someone were to be trying to do this plan, they could carry it out exactly. All right. For the do part, you would perform many repetitions of the simulation. In our AP class, which chances are we're not going to be doing the entire simulation, because for simulations you want to do lots and lots and lots of repetitions. So maybe you'll do 1 or 2 and say, hey, you would continue this. And then based off your results, you would come to a conclusion about your simulation to answer your question of interest. So let's do an example together. Suppose I want to choose a simple random sample of size 6 from a group of 60 seniors and 30 juniors. To do this, I write each person's name on an equally sized piece of paper and mix them up in a large grocery bag. Just as I'm about to select the first name, a thoughtful student suggests that I should stratify by class. I agree, and we decide it would be appropriate to select 4 seniors and 2 juniors. However, since I already mixed up the names, I don't want to have to separate them all again. Instead, I will select names one at a time from the bag until I get 4 seniors and 2 juniors. This means, however, that I may need to select more than 6 names, right? Because in case I get more than 2 juniors before I get the 4 seniors. We're going to design and carry out a simulation using Table D to estimate the probability that you must draw 8 or more names to get the 4 seniors and 2 juniors. Table D is in the back of your textbook, and it's also what people use for a random number generator if they don't have technology. So you start on a row and you go from there. So let's go for the state. What is the probability that you will have to draw 8 or more names to get 4 seniors and 2 juniors out of a pool of 60 seniors and 30 juniors? You're essentially summarizing the problem. What's our plan? We need to assign values, right? 2-digit values. So we can say 01 to 60 can be your seniors and 61 to 90 can be your juniors. Select values from Table D. This is crucial to say. Ignoring values that repeat or are not within our range of 01 to 90. Okay. We're going to select the values until 4 seniors and 2 juniors have been selected, and then you record how many selections were needed. We would do this many times. So let's go through one of our trials. So again, I'm looking at Table D in my book, so if you need your book, you can see that. The first 2 numbers are 19, so that's a senior. 22, senior. 39, senior. So on and so forth. I kept going. We ended up needing to get 8 selections until we had the 4 seniors and 2 juniors. If I did this again, this one took me 11 selections until I got to what I needed. At this point, you would want to keep going and do many trials, probably about 50, so you can get a good case. Because right now, I wouldn't want to just use these 2 and say, oh, out of 2 trials, you're for sure 100% of the time going to need to take 8 or more draws until you get 4 seniors and 2 juniors. So to conclude, if you did this 50 times, about 52% of the time in the simulation, we needed 8 or more trials in order to get what we wanted. Okay? That wraps up this section. Make sure you do some practice problems in the book so you're good with how to interpret probability and also to describe how to do simulations.